Hey chemistry nerds, I wanted to put this video out earlier this weekend, but my boy was having trouble staying motivated and awake this past weekend. But nevertheless, better late than never, here is the acids and bases review. So these are the following topics I'll go over and summarize in this video. We're going to start with electrolytes, then going into the two theories of acids and bases. What is pH, how to indicate pH levels with indicators, neutralization, and titration. So I started this unit with the idea of electrolytes. And they're essentially what acids, bases, and salts are. They're examples of electrolytes. So what exactly is an electrolyte? Examples aside. They conduct electricity due to mobile ions. So if you look at some of these substances, if they can dissolve into ions, then they can conduct electricity. Because the charges don't necessarily have to be negative for electricity to run through. As long as their charges, positive and negative, electricity will flow. So here I'm just going to list some examples of electrolytes, acids, bases, and salts to show you how they can dissolve into ions and what makes them an electrolyte. So let's start with a salt like NaCl. So this is a salt because it can dissolve right here. It's an electrolyte into Na plus and Cl minus. So those are the two ions. Another one common example is LiBr, lithium bromide. If you take a metal, combine it with a non-metal like lithium and bromide, then you get a salt. Same thing with NaCl. So it's Li plus and Br minus. Alright, let's go into, let's say, an example of an acid. So HCl. So the two ions again are H plus, Cl minus. Another acid that we might see is H2SO4, hydrogen sulfate, or sulfuric acid. It splits up into H plus and then HSO4 minus. You could even break it down even further for two H pluses and then SO4 minus. Two minus. Okay, and then let's talk about bases then. Let me use this one. So what is an example of a base? Sodium hydroxide. Can you guys see that? Alright. So this one will split up. Let's use a different color. Let's use yellow. I'm just mashing up different colors here. Not that pleasant, to be honest. And another example, let's say, is lithium hydroxide again. You might see some acids and bases that don't dissolve quite as well. They're kind of on the weaker side, but still, nevertheless, they are considered electrolytes if they can dissolve into ions. So speaking now about acids and bases, we have, starting with our first theory, the Irenaeus Theory, which pretty much focuses on producing ions. And those ions are either hydronium, which is H+, or hydroxide, OH-. So remember those words, hydronium, H+, and hydroxide, OH-. And so depending on which ions are produced, that tells us whether it's an acid or a base. So acids, let's go with red for acid. They produce hydronium ions. Whereas bases, they produce hydroxide ions. So here, let's look at some examples. HCl, HBr, H2SO4 as an example. So when they dissolve in water, if you place these substances in water, they'll dissolve into their ions, and you'll see that there's an H in front of there. That's typically a good indicator that this is an acid. All right, now on the other hand over here, for the bases, some examples. A good thing to look out for is the OH, like right here, oopsies, right here. Sodium hydroxide, lithium hydroxide. Another good one is, if you just look at here, the OH is in there. That's a good indicator that it is a base if you see the OH at the end. However, here is an exception. I'm going to put this in a different color. If you see something like this, while there is an OH at the end, what you want to look out for right here is the carbon. If there's a carbon there, that means this makes it an organic compound. This is not a base. This is an alcohol. And they are not basic. They're slightly acidic. So you want to be careful there. If you see an OH at the end, but there is a carbon, then it's not a base. You want to see those OHs at the end without a carbon to be considered a base. You might see in some other examples like NH, well actually, that will go into the other definition, but yeah. These are some examples of acids and bases following the Irenaeus theory. Now, the Bronsted-Lowry theory will explain why other substances are considered acids and bases, but not necessarily so under the Irenaeus theory. So this is based on accepting or donating that proton. So whether or not they'll accept it or donate it. Let's start with the acid. Acids will donate the proton, whereas the bases will accept the proton. And I'll show you in an example reaction here. So let's say we have a reaction of HCl and water. Okay, so here we're going to see which one accepts and donates the proton. So let's focus on HCl, hydrochloric acid. In its name, it already has the term acid, but what makes it the acid? So we start with HCl. What happens to it? If you notice, on the other side, it just becomes Cl minus. Where did the hydrogen go? So that means it gave it up, making this the donor and the acid. So what does this make H2O then? We start with H2O, and then over here it becomes H3O plus. So what happened to it? It accepted that proton. So if it accepted the proton, that makes it a base. Now if you look at the other side of the equation, you could still have a forward and backwards reaction. That's why we have this right here. That means you could go forwards and backwards with this reaction. That means on the other side of this equation, we also have acids and bases. This is what we call the conjugate acid-base pairs, if you remember. So looking at the other side, let's start with this, H3O plus. What did it do to become that? Or actually, let me rephrase that. What is it doing going from the backwards reaction? So we start out with H3O plus, and then it becomes H2O. What did it do? It gave up the proton. So in this case, H3O plus is the acid. And that's typically also an indicator of acidity. If you want to look for acidity, you look for H3O plus. Next, we look at Cl minus. What did it do? went from Cl minus to HCl. So what did it do? It accepted the proton, making it the base. All right, now let me do another example. Let's use purple. All right, so NH3 and water. You're going to notice here that water is going to play a dual role. It can be either an acid or a base. So in this example, we're going to see water act as an acid. All right, now here, NH3. You'll see it on one of the tables that's listed under common bases. But if you look at the Irenaeus theory, does it produce an OH minus ion? It doesn't, but under this theory, it could still act as a base. And you'll see why. So let's follow NH3. So NH3 starts off just like this, and then over to the other side, it becomes NH4+. What did it do? It accepted the proton. That's why it's a base. So ammonia becomes ammonium. Now here on the other side, so if NH3 is the base, that makes H2O the acid. But how? What did it do? H2O became OH minus. What did it do? It donated the proton. It lost the proton to become OH minus. So that makes it the acid. So notice here between examples 1 and 2, we see that dual role between acids and bases for water. Now on the other side, NH4+, going backwards, it went from NH4+ to NH3. That makes it the acid. It gave up the proton to become NH3. That leaves OH minus to be the base. If you also notice, it accepted the proton to become H2O. Now, how do we sort of rank acidity and basicity? So this is what we call the pH scale. And it runs on a scale of 0 to 14, 0 being the lowest and 14 being the highest. And this specifically measures the concentration of hydronium ions. So let's remember this keyword right here, hydronium. Conversely, there's something called pOH, and it's the reverse of this. It measures the hydroxide ions. And it's still 0 to 14, but that's something we don't need to know. Because here, we mostly use pH. Acids and hydroniums matter. All right, so based on the scale, how do we know if something's acid, neutral, or base? So acids have pH levels that are less than 7. So 7 is our midpoint between 0 and 14. So if it's less than 7, it's going to be acidic. Now for neutral substances, that means it has to equal 7. Typically water is a good example. It can be slightly above or slightly below, and it still be relatively neutral. The bases now, they have to be above 7. So anything greater than 7 is considered basic. All right, so to put this into perspective, some relationships here. So lower pH means greater acidity, and over here, higher pH means higher basicity. Now in terms of hydronium concentration, that means this has high H plus concentration and low OH minus concentration. Remember, increasing the acidity means we have a lot of hydroniums and very little hydroxides, and that means a lower pH. It's kind of hard to put that in perspective because we're thinking usually associating it the other way around. Whereas here, we have low hydronium concentration and high hydroxide concentration. All right, math of pH. How do we even calculate for this? So there's this equation right here. This beautiful equation you might even be afraid of because it has log. So we take the negative log of the hydronium concentration. So as an example, that was an ugly writing. Okay. So if our H plus concentration is equal to 1.0 times 10 to the negative fifth molarity, that means we could have, you plug this number in into the equation within those brackets, and you get a pH of 5. I'm going to show you another example here. If we have 1.0 times 10 to the negative 2 molar, plug that in, we also get a pH of 2. Now if you notice here, look at that exponent. Look at that beautiful exponent. We have a negative 5 over here, and we have a pH of 5. We have a negative 2 exponent here, and we have a pH of 2. That is our shortcut, but that's only if right here. I'm going to circle it. That's only if this part is equal to 1. And the examples you'll see on the test will only deal with 1. So you don't have to use this equation. Just remember the shortcut. You look at that exponent, drop the negative sign, and you get the pH value. All right. Now there's this other part about this that we really need to crack down on and get good at. And that's called the concentration factors. So if you actually calculate this, let's go back to our examples. That means this is not too acidic over here, and pH of 2 means really acidic. This has a higher acidity than the other one. If you actually look at their concentrations right here, let's actually put that into numerical form instead of scientific notation. So if we look at example 1, 1.0 times 10 to the negative fifth molarity, that means we have a concentration of this. Oops. And then over here, this other one is I keep messing this up. There we go. If you compare the numbers, it's clear that the second example has a higher concentration of hydronium ions. So if we have more hydroniums, that means we have a higher acidity and therefore a lower pH number. That's why if you see that pH value is lower, but it shows that it's more acidic because it has higher concentration of hydroniums. Now, by how much is this? How much greater is this than that? So let's make a note here. How different are these? So what is the factor? How do we even figure this out? So if we take the pH values, so pH values, so we go from 5 to 2. That's a pH difference of 3. So 3 pH units. And to figure out the concentration factors, we're going to go here. I'm going to show you this equation. So 10 to the 3 means 1,000. So our pH in the second example is 1,000 times greater than the first one. So pH of 2 means it has 1,000 times greater concentration, 1,000 times more acidic than the first example with a pH of 5. So here, 1,000 times more acidic. So to sort of summarize what I pretty much did in the previous slide, so if pH is going down, that means we're increasing acidity and also increasing H plus or H3O plus. Whereas if pH is going up, basicity or acidity goes down and this goes down. So first example, if we're going from a pH of 6 to 4, that means we're becoming more acidic. That means we should see an increase in H plus. By how much? So this is a pH difference of 2. So this is 100 times greater. Now in our second example, if we increase our pH this time, going from 3 to 7, so we have a decrease because we're becoming more basic. Decrease in this. So going from, so we get a pH difference of 4, 10 to the 4th is 10,000. 10,000 times less. Okay, those are some examples for you guys to mull over. Now looking at our solutions, they can be pretty clear and colorless. Now how do we tell if something's acidic or basic? So this is what we have. We have indicators. They pretty much tell us by the color and the color changes. Because some colors indicate certain pHs and other colors indicate a different kind, whether it's acidic or basic or somewhere in the middle. And the two most common ones we use are phenolphthalein, which is, if you notice on the table, colorless to pink. So colorless meaning acid, typically. And then pink for basic. And then litmus paper can be red for acid or blue for basic. But looking at our table M, we need to know how to use this table. We have different indicators, and they give us the approximate range for color change. That means at any point within this range, it could change color. So a pH in between here could mean it could either be red or yellow. It doesn't necessarily have to be strictly outside the range to be red or yellow. So anywhere within this range could also fall under the color changes as well. So taking a look at methyl orange as our example, if you have something below 3.1, then for sure it is red. And if it's above 4.4, then it's for sure yellow. You could still have something that's red that's within the range or yellow that's within the range. It's approximate range. Okay, now we come across neutralization. And this is a reaction. It's a type of reaction between acid and a base. And they always produce water and a salt. And during neutralization, in order for it to occur, you need to have equal moles between acid and base. So equal mole, let's say 1 mole of an acid is reacting with 1 mole of a base, then it's a complete neutralization and you get water and a salt. And this can be performed through titration, which we'll cover in the next slide. So here I'm going to give you guys the bare bones skeleton of a neutralization. So a neutralization is basically acid plus base yielding water and salt. And so I'll list some examples below right here. So a good example, typically, you'll see is HCl plus sodium hydroxide yielding H2O and the salt NaCl. So when they ask you to complete these neutralization reactions, you should always put water first. That's for sure going to happen. Now, how do we figure out the salt? So here, we get the H and the OH here. They make water. So that leaves us with the Cl and the Na. So you combine whatever's left over to get the salt, NaCl, which is our table salt. Now, how do you know which one's the acid and which one's the base? You could always check the reference tables for that. But here, when completing neutralization reactions, it doesn't really matter to distinguish between the acids and the bases here. But just know how to complete neutralization reactions. And let's think of another one. Let's try H2SO4 plus calcium hydroxide. As always, we have H2O. Alongside that, we're going to have our leftovers, SO4 and Ca, right here. They're going to combine to make calcium sulfate. And that here is our neutralization reaction. Titration now is our process, and this is the math part of this unit. The lab process to react acids and bases together. It's where you can mix a known volume of an acid with an unknown volume of a base, so you can figure out how much volume of base do you need to react with this specific acid. And then before the reaction even begins, you typically put phenolphthalein inside the acid, so that once you add enough base, then the color change will happen. And once that color change happens, that's when you know you hit the endpoint and neutralization. So marked by color change. So it typically starts out colorless and clear, and then once the solution completely turns pink, that's when you hit the endpoint and neutralization, which is where you have equal moles of acid and base together. And so this leads us to this equation. This is a neutralization titration equation. So this equation assumes that we have equal moles of acid and base. That's in order for neutralization to occur. So here MAVA equals MBVB. This is in table T, in case you don't remember this. So what do these variables mean? Alright, so this is concentration of acid. Note that A stands for acid and B stands for base. So acid on the left, base on the right. Volume of acid. And likewise down here, concentration of the base. And then volume of base. And the units we use for these, M for molarity, ml or liters, milliliters or liters for the volume. So in order to know which one is which, make sure you check the units. Milliliters or liters, you should know already by now that that's a unit for volume. I can forgive you for not remembering the unit for concentration, but by now you should remember that milliliters and liters are the units for volume. So problems you'll see are pretty much plug and chug. You look at the question, list down what you're given, plug it in, and solve for the missing value. And these problems will always give you three values, and you solve for the fourth missing one. Now, a common question I've heard throughout this unit is, I don't know which one's the acid or which is the base. So what if you can't tell? So here's some tips I'm going to tell you guys. Acid, I want you to check table K. And then for bases, you're going to check table L. So that's one way. Another way you could check, let's use a different color. Look for the H plus, I want you to look for the H in front. What do I mean by that? HCl, HBr, H2SO4. Those are common acids. You might even see this one. And it sort of sometimes might even look like this. So at first glance, you might even confuse this for a base because of the OH, but remember there's carbon, so it's not a base. So that one happens to be in the reference table. It might not look like it at first, but always check the reference table in case you're ever confused. But another good indicator is look for the H in front. Now likewise on the other side, you want to look for the OH in the back. So sodium hydroxide is a common one, lithium hydroxide. You might even see this one, ammonia. So that's in the reference table, you want to look for that one. So also remember exception. If there's an OH in back, but carbon is present, this is not a base. This is typically important for you to know, especially when solving problems with pH values or even doing that titration problem. Alright, now we've reached the end of the video, and all I could say to you guys is to study, make sure you review these things, and good luck.